Hi, I'm Scott Chamber from BFI Bullion, and I've been given the pleasure of announcing this very fascinating fireside conversation between Thomas Pedersen and our own chairman, Frank Seuss. Copenhagen Atomics is a Danish startup company that wants to revolutionize the energy sector. Their thorium molten-salt reactors produce energy in a safer, more efficient, and much cheaper way than traditional nuclear plants, or other energy sources for that matter. Not only is the technology they are working on unique, but so is their business model. Contrary to nuclear plants we are familiar with today, the Copenhagen Atomics approach entails mass manufactured reactors, each the size of a standard shipping container. Thomas explains how their technology works, where in the business development process they are, and what challenges and opportunities he expects in the future. Listening to this conversation, I'm sure you, as I did, will realize how quickly nuclear technologies have advanced and how much they differ from what most people still associate with it. I was certainly guilty of being stuck in thinking of nuclear power in terms of the 3 Mile Island, Chernobyl, and Fukushima incidents. There are certainly very exciting developments out there that are worth learning about, especially because, and in using the words of Copenhagen Atomics, energy equals prosperity. I hope you enjoy this conversation, and as always, please like, share, and subscribe.
So, Thomas, welcome to Switzerland. It's great that you're here.
Thanks.
I'm actually really excited about this conversation with you. I've been watching Copenhagen Atomics for several years now. I've watched you on YouTube a few times, and the first time I watched, I was intrigued, and then as I followed and looked into nuclear technology a bit more, I just became more and more intrigued with what you guys are doing at Copenhagen Atomics. So I really look forward to this meeting. It's also a fact that if you look at everything that's going on today, there's quite a few things that are maybe not headed in the right direction. And one of them, in some countries particular, is energy policy. And on your T-shirts, you guys put it very much to the point where energy equals prosperity. And I think that is so important. I mean, we cannot do anything without energy in a modern society. So really look forward to discussing what you guys have done with Copenhagen Atomics. Maybe to get started, just if you could explain at a high level, for the layman's like me, what is special? What's the paradigm shift in nuclear technology that Copenhagen Atomics has actually been able to achieve so far?
Yeah. So we're trying to build a new type of nuclear reactors. They run on thorium. That's a different fuel than all the sort of classical reactors run on pure uranium. But then also they are called molten-salt reactors. So it's a liquid fuel form instead of solid fuel. In all the classical reactors uses solid fuel. So there's a number of very important differences that makes the nuclear process very different and much more efficient. And that also means that the energy that we can generate will have much lower cost than traditional nuclear energy. And what we are trying to do with the company is also making it possible to build these reactors much faster. You might know that we humans have built nuclear reactors now for 70 years. And in the beginning, back in the 50s and 60s, we were able to build those reactors in 1 or 2 or 3 years. Now in the West, in Europe and North America, it takes 10 years or more to build a reactor. So it sort of became slower and slower and more expensive. And we want to change that. We want to sort of bring something new to the table where we can deploy this technology really fast, build one reactor every day. That's sort of the mantra right from the beginning when we started the company. We said we want to build one reactor every day, and then of course we want to bring the price down. The price point is sort of inherent in that we use a completely different technology. So the technology itself helps drive down the price. The size of our reactors is roughly the same as a 40-foot shipping container. So it's also a very different size of the machine than what you see from classical nuclear. So that's maybe the quick introduction.
So basically, I think you mentioned that also earlier over lunch, is that the common narrative is really that nuclear reactors, nuclear energy is expensive. It's financed by tax money. It's takes a long time to market, to build. It's big infrastructure, lots of cost, and it's also focused very much on the electrical grid. And actually, what you guys have built is very different in all those aspects, I guess.
Yeah. Yeah. From the beginning, we wanted to be different.
Yeah. So I guess when it comes to the aspect of safety, which is also one which is, in the common narrative is nuclear is dangerous. First of all, that can be debated, and we can get into that. But secondly, with your technology, why is your technology, how is it different and how is it safer than the current light water reactor technology?
Yeah, so the traditional solid fuel reactors, that many of them are called light water reactors, and they are controlled with these control rods that you pull in and out. And basically those rods are controlled by humans, and they regulate how much energy you output. And then if there's some accident and you don't adjust those correctly, then you could have a situation where all the water boils off and then you have a meltdown or something. But this has been used in the media as something really, really dangerous. But actually a meltdown has never killed anyone. So it's sort of it's not really dangerous, but it's in the media it's projected as being dangerous. That doesn't mean that nuclear power is not dangerous at all. It just means that there's a lot of misunderstandings in the way the safety or risk scenarios are communicated in the public media.
So if you say it's never killed anyone, I mean obviously the most recent or the second big accident was Fukushima. And if you actually listen to the media, they tell a very different story. You get the impression that thousands of people died, which I guess had nothing to do really with the nuclear reactor, though.
Yeah, so there was a natural disaster with the earthquake and tsunami, and the tsunami killed a lot of people on the same day. Right. But that has nothing to do with the nuclear power accident. The power accident was very costly. There was several hydrogen explosions that destroyed some reactors, and that meant they couldn't cool the fuel, and some of it melted down, and it's very expensive to clean up. But all of that didn't kill anyone, but the evacuation killed some people. And you can say...
How did the evacuation kill people?
Well, so some people were old and fragile and in hospitals, and they were evacuated, and they, that was too stressful for them, and they died. That's very unfortunate. There was also some people who died in traffic accidents from driving, like they were really scared and then got in traffic accidents. And then most of the people died from just, upending their whole life and moving them away from where they used to live. So they lost their job and started drinking alcohol or whatever. So they got sort of those type of diseases related to the movement. And many of them have still not been able to return now more than 10 years later. That's very tragic, and most of those
So they're not able to return because of radiation, or why are they not? Just because of economics, or because the radiation is not that high anymore as far as I understand it?
Exactly. And there's a lot of debate about this, and I don't think we can cover all of it here. Right. But it's clear that if we had kept all the people there, a few might have died from cancer related to radiation. But I think everybody agrees that if we had not moved the people, overall less people would have died in total. I think that's not debatable. But there's of course a debate about if there is a risk, should you then move people? And maybe they should have moved less people. And there's all these different scenarios. And of course those decisions to move people were taken very hastily in the midst of this whole tsunami scenario. Yeah. And it's okay that politicians or people in the government make mistakes in such a situation, but it's important to say that it was not the nuclear technology that killed those people. It was the authorities that made wrong decisions in the evacuation scenario, and also in the aftermath where they didn't want to move them back. And there's a lot of debate about this, and it's just a sad story altogether.
So to be clear, there's a debate around, you know, what happened there, you know, how bad or what was, whose fault was, etc. But I think important for our purposes to say that this could not have happened with, I mean, you mentioned, for example, hydrogen explosions. That is something that could not happen with Copenhagen Atomics technology. Is that correct?
That's correct, but there are some people who say, oh, but these new reactors, they can never make an accident. And I think that's too, you know, that's a wrong way to put it. I mean, I think we've shown over many decades now that nuclear technology is super safe. It's one of the safest form of energy we have. And now there's a new type of reactor, and maybe it's slightly more safe than the old type of reactors. But we don't really know. We need to run them for many decades before we can really say for sure. And we are really down in the tiny numbers, you know, part per millions or something. So when you're down there, it's sort of, I don't think it's reasonable to try to sell it to people as more safe. But what we can say is that it's much safer than the other types or other forms of energy that we build. So if we don't build these type of reactors, we will build something else, and that something else is 100% sure more deadly or more unsafe than what we bring to the table. So no matter what, it is safer than the alternative.
We flew over the technology itself a bit. So there were a few things you mentioned. One is that you know, you're using thorium. I think there's also some uranium that you use. Maybe to explain the difference of the typical reactor today to your technology, you have something called the onion core. Could you describe a bit for, you know, in simple terms how that works and what's different to other reactors? Yes.
So I want to start with the classical reactors because that's sort of what people know today. And in those reactors, you dig mostly uranium out of the ground. And then most of the reactors, you have to enrich the uranium before you can use it. But in any case, you put that fuel into reactors as solid fuel. I mean, that's in sticks.
These fuel rods.
Yeah, fuel rods that are, and it's solid, not liquid. And then you can run that reactor for some amount of time, depending on the different designs, but typically for 1 or 2 years, sometimes 3 years. And then you have to replace the fuel. So you take it out and call it spent fuel. And then you take some new fuel that you have dug out of the ground and you put that in. And sort of the sorry state of that whole situation is that you're only able to burn or generate energy from less than 1% of the uranium that you mine out of the ground. So it's a very inefficient process. And at the same time, this spent fuel, it's considered by many people as nuclear waste and very dangerous. That's not the entire story, but at least that's how it's talked about in the media. And how our reactor is different is that.
So, but just so what is so you're saying only 1% of the fuel is actually used in the old technology?
Yes.
So 99% of the fuel is not used and goes into end storage.
Yeah.
And you're saying, why are you saying there? So you're saying only a small part of that spent fuel rod is actually problematic? Is that what you said?
Yeah.
In terms of end storage?
Yeah, that's also a thing in that in those fuel rods, there's all kinds of different elements mixed, and some of them are highly radioactive, but most of it is not dangerous. I mean, the majority of it, like almost 90% of that is uranium, and it's exactly the same uranium as what we dug out of the ground. Yeah, so it hasn't changed at all. And there's actually people showing that you can eat that without dying from it. So that shows you that it's not dangerous. Of course, it's not healthy to eat a lot of it, just like you shouldn't eat a lot of lead or aluminium or steel. Right. But you can eat a little bit of it without dying. So it just shows that it's...
Without dying or also without getting sick?
Also without getting sick.
Okay.
Okay, so it's sort of the last 5% is what is problematic. And the most radioactive part of that is called fission products. Yeah. And well, it's expensive to separate these things, and that's why we don't do it. There's one country, France, they actually do separate it.
They recycle it?
They try to recycle it, and it's not super great economics around that recycling, but at least they do something about it. most of the other countries doesn't do anything. They just call it spent fuel or sometimes nuclear waste. But it's actually really valuable. That's the other thing. I mean, my opinion is that spent fuel is more valuable than gold or diamonds in terms of weight. Yeah. So even if some countries end up burrowing it down deep underground, we will eventually dig it up within the next 100 years.
You think as technology evolves and we can reuse it in a better way, you think it will become very valuable?
Yeah, we will dig it up again. We know exactly where it is. Normally when you mine for things, other material, gold or something, you don't know exactly where it is, and you have to mine all this material out of the ground to find the gold. Yeah. But here we know exactly where it is, so it's much easier to find it.
Right. Interesting. So going back to the onion core.
Yes.
And this mix of thorium with uranium, how does that work?
It works in a different way, where suddenly you can use almost all the thorium and uranium that you dig out of the ground, at least 90% of it. So you need much less mining to generate the same amount of energy. So of course that's very important, because the mining part and the processing of all that material and the transport of all that material is expensive. Yeah. So when we can cut that down by a factor of almost 100, and that helps a lot on the energy price. That's sort of the most important thing. One of the other things that is important is that in a solid fuel reactor, all the old reactors, you cannot remove those fission products while the reactor is running. And those fission products is what makes it inefficient, that they capture a lot of neutrons, and that's why you can only burn 1% of the fuel. But in our reactor, in the onion core, you can actually remove those fission products, because it's a liquid fuel. So it's a liquid that you pump around, and then when you pump it around, you can have filters that remove those fission products, and therefore you get much better fuel economy and can use the fuel more efficiently. So that's a very important point. And then the sort of the final thing is that we have what is called a thorium blanket. It's basically, that's why it's an onion core. But the outer layer of that onion, the onion has several layers in order to function, but the outer layer of that onion is a thick sort of sheet of, you could say it's thick like this, 20 centimeters thick, made out of thorium, and it's also liquid. So it's again a molten salt that you can pump around. But that thorium blanket captures a lot of neutrons, and this is how we upgrade thorium, which is not a fissile fuel. We upgrade that to become a fissile fuel that we can then use inside the reactor core. And this has not been done before. I mean, it has been done in theory, but nobody has ever built a machine like that. And that's our invention, this onion core, and how to move the thorium from the blanket into the core. It has been proposed in the past. It's not like we came up with the whole idea, but the actual implementation of it and this very efficient way of making the onion core with this thick blanket is our invention.
So this onion core, what is it, like 1 meter by 2 meters, or how big is it?
It's roughly 2 meters in diameter. It looks like a big giant ball.
Yeah. So a giant onion.
Yeah.
And what you're saying is that, so there's obviously it's steel, a special material, because I think with those molten salts there are corrosion issues, or have been, so it must be special material that you guys are using. Then you say there's this thorium layer, which is also liquid, right? So it's a liquid. And then what's the next layer?
Yeah, so the outermost layer is a thorium molten salt. Yeah. The next layer, if you go in, is a heavy water. So it's almost like regular water, but heavy water
is D2O, or?
Yeah, D2O, exactly. Okay. And it has some better neutron economy. That means that it behaves differently with the neutrons. It doesn't capture as many neutrons, and has a different way of slowing them down. That's why it needs to be heavy water.
So the purpose is slowing down the neutrons?
Yes.
Okay. And then the next layer is,
then the next layer uranium then, moving in is the fuel salt. That's where the magic happens, or that's where the energy is created. That's actually a very thin layer. It's only a few centimeters thick.
And when you say fuel salt, what's in the fuel salt?
Yeah, you can have different things in the fuel salt. In our very first reactor, it's going to be lithium fluoride, uranium fluoride. So lithium is the same as what you have in batteries, right. And fluorine is like a gas. You can find that in toothpaste.
Okay.
But
Fluorine, yeah.
So you have lithium fluoride and then uranium fluoride, and that generates a salt, which is a liquid at these temperatures around 600 degrees, and it has roughly the same viscosity as water, but it has much higher density. So each liter weighs around 4 kilos, and then because it's a liquid, you can pump it around, and you pump it really fast. So it has to. That's sort of.
So that's what heats up.
Yeah.
Is that layer?
Yes. Yeah. Exactly.
And so the thorium layer is not fissile at all in this structure.
No, it's called fertile. That means that it's capable of capturing neutrons, and that's sort of the whole idea. In classical reactors, you don't have that blanket. So what happens is you lose a lot of neutrons. They just fly out of the reactor, and they are lost, and they actually cause damage outside the reactor. But also they make the fuel economy or the neutron economy of the classical reactors much worse. Just because we have this blanket, which is really good at capturing neutrons because of the way we have constructed it, we have very little neutron leakage to the outside. And that's also what helps keep the efficiency high. And then slowly, that thorium in the blanket is converted to something called uranium-233, which is then become the fuel in the fuel channel.
So you then use it to put it into the liquid fuel part?
Yeah, yes.
And the liquid fuel part then is a mixture of, I guess, thorium-233 then and uranium, or what is actually in there?
No, so the thorium stays out in the blanket.
Yeah.
But in the fuel channel, it depends a little bit on what you choose as a fuel. Yeah. But in the first reactor we want to run, we will use what is called 5% enriched uranium. So that means there's 5% uranium-235, and then there's 95% uranium-238, which is, you cannot use that directly, but eventually a small amount of it will turn into plutonium, which you can use. And then slowly we move this uranium-233 from the blanket into that fuel salt. And so you can see the composition of those different types of uranium changes over time as you burn away the uranium-235 and you continue to add more and more uranium-233.
But so the recycling of the spent fuel actually happens
that's a different story.
Is that a separate process?
Yeah, so in the first reactor we want to test, we don't want to use spent fuel because it has been too difficult for us to get to be allowed to take spent fuel and process that and turn it into fuel salt. We want to do that, but it's not going to be in the first reactor. It will be a little bit later once we have all the approvals in place. But it's essentially, I mean, in that case, we just put the spent fuel in that fuel channel instead of the 5% enriched uranium.
So for me, this is all very difficult to really understand because I think there's a lot of physics and chemistry and so on. Yeah. But even with these salts, it seems it's very complex. But if I understand correctly, so the fuel, the smallest volume part, actually, that's the part that you could actually just, in a case where you wanted to stop the reactor, if it became too hot, I believe, it just flows into like a safety bucket, or what do you call that? Yeah,
so in our reactor design, we have a number of tanks, just basically square tanks like buckets below the reactor core. And the way it's constructed is that if any of the pumps inside the reactor stops, then the reactor stops, and then we stop all the other pumps, and then all these different salts will drain into their respective tank or bucket.
As soon as the circulation stops, it basically automatically flows into those buckets.
It automatically.
And then it can't react. There can't be any kind of meltdown or any of those scenarios that we're concerned of. Yeah. There's no cooling required at that point either.
There is. You do need to cool those tanks at the bottom.
Okay.
Because there's what is called decay heat. So the salt will continue to generate decay heat, and you need to remove that. That's the cooling.
I see.
But the chain reaction stops as soon as you stop one of the pumps. Within a second or maybe 2 seconds, the chain reaction stops, and then you don't generate new energy. So when you dump the salt in those tanks, there is removal of that heat, and that is passive decay heat removal. That means that there are circulation of air, so the air removes the heat, but that air is not driven by a fan or anything. It's just
the
natural
circulation.
Flow. Yeah.
Okay, I get it. So actually, there's a passive, a kind of a passive cooling process. So
Yes.
you cannot really have that kind of catastrophe in terms of that the thing blows up or there's a meltdown or anything. That's very different from light water reactors, I guess, where you have pressure and where the cooling has to be artificial to some degree.
Yeah. Yes.
Okay. It's much safer. On the cost side, going back a bit, I mean, one of the things that you said before, the paradigm shift comes with the fact that, the cost of this will be much lower. And what fascinated me when I heard about it the first time was the fact that you guys are actually interested or have, your concept is one of mass manufacturing. I don't know if you can get into that a bit, because that really changes the whole ball game. I mean, being able to create that onion core at a much smaller size allows you to put it into those containers.
Yeah.
And that creates that possibility to then mass manufacture in Copenhagen in the beginning at least, right?
Yeah, yes. Yeah, of course, that's one of the goals here is to, I mean, in this world we already use a huge amount of energy, and there's even more people who will like to have access to running water and air conditioner, refrigerators and transportation. But likely in the future we need even more energy. Many people talk about that the world needs to double the amount of energy before 2050, and that's of course a big question. Can we even do that? But it's clear that if nuclear energy has to even double or triple, there was talk at this last COP28 that some countries agreed that they should triple nuclear energy. I mean, that is a huge challenge to triple that, and we actually want even more than tripling. We want more energy because nuclear energy is safe and it's green, and then in our case, of course, we want to make the lowest cost of energy. You know, it should be cheaper than wind or solar or coal or oil or gas or fusion or anything. And once you have an energy source that is very low cost, then hopefully a lot of people want to install that. And then the problem becomes, okay, how quickly can you scale this up? How quickly can you go from building one every year to building one every day? And that's sort of a mass manufacturing challenge, just like it is when we mass manufacture cars or airplanes or iPhones or whatever. And that hasn't been done before. Nuclear reactors was never mass manufactured. It was always something you built it on site. It's this big construction project. There's a reactor in the UK now called Hinkley Point C, and that whole building site has 5,000 employees. Like it's really difficult to make such a on-site construction highly efficient, and that's also why it takes 10 years. So we try to turn that thing on its head and said we want to mass manufacture this just like cars or iPhones or whatever, and get them out of a factory. And then the problem becomes, okay, that's fairly easy to do that. But it's actually not easy to install one reactor every day somewhere in the world. That's a huge challenge. And of course, that's what we are sort of on our way to solve.
So to think of this really, I mean, you figure out the mass manufacturing, the transportation, the setup, but then once you have that figured out, you can basically scale or calibrate to the needs of whatever use case you're actually looking at. And I think that's also where you guys are taking a bit of a different approach, where generally the narrative is one where you immediately think of the electrical grid, right? But actually electricity is a smaller part of what we do, at least today, but maybe also in the future with energy. Your technology actually could also use the heat so that you could use all kinds of different use cases. What kinds of use cases do you think are most interesting for your technology?
I would say definitely the commodities, things like ammonia and aluminum, steel, concrete, all kinds of what's it called, like refineries. When you do refineries where you make, of course, a different gasoline and diesel, but you also make different chemical products in refineries. And in general, like chemical factories, a lot of those need high temperature heat for distillation and such processes. And then, of course, there's mining. We humans use a huge amount of energy in mining. Sort of digging all that dirt out of the ground, crushing it and sorting it. If you're mining for gold or uranium or copper, you need to mine, millions and millions of tons of dirt out of the ground, crush it and separate it. It's really expensive, all this processing, and it's energy intensive. And
but
today, most of that is
how would you do that
fossil
now with your technology? Are you saying you would create ammonium or hydrogen to then run the machinery that today is run maybe by diesel, or?
Yeah, that is also a possibility, to just replace the diesel in the mining operation with ammonia, for example. But it's also an option to put a nuclear power plant at a big mining site and then convert some of the heat into electricity and run all the moving equipment with that electricity, and then use some of the heat for the smelting or whatever is needed at that mining site.
So you could create like really large plants that would create tons and tons of ammonium or hydrogen.
Yeah.
But you could also actually have a smaller use case for an industrial plant where you would have maybe 2 or 3 modules. Is that correct?
It is technically possible to put one unit at a time at a factory somewhere. But to be honest, in the beginning, I think the world is not ready for that. All the approval processes and the international guidelines on how to regulate nuclear energy is not ready for single deployment. I think that will come sort of further down the maybe after 2050.
If it wasn't for the approval process, your technology though would actually be ideal for those kinds of decentralized use cases.
Yes,
right?
correct.
Okay.
But
that's a big game changer too. I think.
Yeah, but I think at least we try to be realistic and say this is sort of a second or third tier deployment case. In the beginning, it makes a lot of sense to go after those industries that needs as much energy as a whole country. We talked about some plants that I mentioned use as much energy as the entire country of Switzerland or electricity. So just one single plant or factory can take 50 or 100 reactors at one site. And I think this will be the first deployment case, that there's maybe 100 of those types of factories around the world.
How much does one module, so one shipping container, how much does one reactor actually create? I mean, do you already know that, how much it can?
So the commercial reactor is generating 100 megawatts of thermal energy, and then if you convert that into electricity, then you get roughly 42 megawatts of electricity per unit. And then, like you said, you can put as many units as you want on a site.
Can you stack them vertically, or do they have to be?
Not in the way we have implemented it.
So it's you need.
Yeah, we
space.
put them next to each other.
Okay.
But it's not entirely impossible. It's just the way we have chosen to do it.
Right.
They are put in a long array next to each other.
Right. So if I imagine like a big plant of a gigawatt, it would look kind of like a flat, large warehouse, or and you would have cranes and everything inside to replace.
Yeah, okay. I mean, most people wouldn't know that was a nuclear power plant. They would look at it and it looks exactly like any other warehouse, and every city in the world has many warehouses in the sort of the outskirts of whatever city.
Is there steam going to be coming out of the plant?
No, not really. I mean, just like there's many office buildings have air-conditioned units, we also have stuff like that, but there's no smoke or no steam or anything coming.
Okay. Interesting. So let's say one of those big plants is there. How often? How do you actually maintain those reactors? Do you have to replace them frequently, or?
Yeah. So some of the parts inside wear out, pumps and heat exchangers and some other like that. Onion core also has a limited lifetime. And in the beginning, we believe that we will replace them every 5 years.
The whole module, or just parts of it?
It's really, really expensive to do service on something that is radioactive.
Right.
So we have decided that it's a better economic case if you replace the whole reactor container. We will keep it inside the building, so that reactor building, there's room to store those used containers, and in the end of the building, you can stack several hundred of those in the end of the building.
Right.
And then we bring in a new one. So you could say every 5 years we bring in a new one, and install it, and then load the salt. The salt is what contains the fuel. So the salt is reused. That can be unloaded from the old one and loaded into the new one, and then the new one can start running.
Okay, so the old module won't actually have any more salt, molten salt in it. You'll actually empty that old module. So it's really the steel,
it's sort of an
the
empty
machinery
steel,
kind of that stays there.
yes.
Okay, interesting. The one of the things I wonder about is the fact that, I mean, I think that's the way you guys want to do it as per default, is the fact that, I mean, normally reactors are financed by tax money, by governance. Therefore, you're going to have a process where the financing has to be approved and so on. In your case, you actually want to do something similar that we know from software as a service.
Yes.
You actually have a model of energy as a service. So that means basically, if I understand it correctly, I have to provide the whatever the land and the connections to either generators or the factory that uses the heat. But the rest is all taken care of by you, and I have a running cost, which is very, very clearly budgeted. So I don't have that uncertainty of not knowing what the construction is going to cost and so on. Is that correct? Or?
That's correct. That's also one of the sort of innovations, or one of the things that we changed from the classical nuclear industry to what we propose is, like I said, we prefer to use our energy sources for production of commodities, aluminium, mining, all these types of customers. Yeah. And those customers, if you are in the board of an aluminum company or a mining company, you might not want to own and operate a nuclear power plant. I mean, that's not what those companies are good at. Right. They are good at making aluminum. Right. So that's where we come and say, okay, we will own and operate that reactor on your site, and we will take care of everything related to the nuclear plant. We will also, after its end of life, we will take it down and recycle all the components and decommissioning, and then give the land back to you when it's...
So it's a full life cycle...
Yes. And that also
service approach,
that also means that we will finance it.
So, I mean, how are you going to do that? Do you already have the deals in place with banks and so on?
Yeah, no, it's too early. It's
okay,
sort of coming down the line. But think of it this way. So no matter whether we were to build and finance it or somebody else have to build and finance it, it's still the same cost that needs to be financed. Right. And the people who finance that, they look at the cash flow. Is there a cash flow that can actually pay back those loans? And so they will, of course, look at that factory. Let's say it's an aluminum plant. They will look at that aluminum plant and say, will that company continue to run for many years? And can the cash flow from that, production of aluminum, can that pay for the reactors? Right. Because if it cannot, then it's too high risk to give a loan to this factory. So it's a long-term contract, and the security is in the belief that the world will continue to use aluminum, and if you cannot sell it locally, you can easily ship it somewhere else and sell it somewhere else in the world. And that's also why it's a good idea to go for commodities, because you're not necessarily influenced very much on local politics. I mean, whether the local economy is up or down, it doesn't matter. As long as the world needs aluminum, you can pay back the loans for that nuclear reactor.
It's actually because of the clear cash flow situation, it's a pretty straightforward present cash value situation to actually evaluate that project.
And there's hardware there that you can secure the loans against.
If we look at, basically you're going to have to scale up the production. Let's say you're now at scale. What is a megawatt going to cost? I mean, how would you compare the cost that you expect and have estimated now? And you're big in mathematics and modeling and simulations and so on. What cost did you actually come up with? What's like that target?
Yeah. So again, we're not going to be the only one supplying nuclear energy, and we look at the market and we believe most of the other players will try to supply electricity for government-controlled electricity grids. So that's where most of the competition is focusing. Right. And they have a certain price point in that type of market. But since we're going after all these commodity manufacturers, there's a different price point, and we have to meet those lower prices. They are lower, but the great thing about our technology with this very much more efficient use of the raw materials and the use of thorium, it means that we can actually provide it at lower cost. But of course, in order to get there, we need to have customers where we can make long-term contracts and where we can run at 100% power most of the time. So when you provide electricity, it sort of goes up and down, and if there's a lot of wind and solar in that grid, then it's even more up and down, and it becomes difficult to predict how much money you can make from that plant in the next 10 years. But if you're supplying energy to an aluminum plant, and it needs, that whole plant needs a certain amount of energy day and night for the next 25 years or whatever. So you know exactly how much energy you can sell, and you can make a contract on that upfront, and this removes some of the uncertainty, and therefore you can sort of get to a lower cost. Also because you never go idle, you go like full steam all the time.
Right.
And so we believe that we can get the price down to $20 per megawatt hour electricity. So that we try to give the electricity price so that you can compare to other forms of energy. And if we look at the sort of the different players in the nuclear industry today, they can provide nuclear power plants at an electricity cost from some of the best ones from $60 per megawatt hour, and some less good up to $120, $130 per megawatt hour. Right. Where we are down at $20 per megawatt hour. So we are like really far away from the traditional model. But of course, there's a number of requirements that come with that low cost. First of all, it only works with those customers who can make a long-term contract. It's a requirement that we can get approval to a sort of a type approval, so that we don't have to make a new nuclear license every time we install a new reactor. We need to have some sort of...
Each time you put in one of those modules.
Yeah, we need to have some sort of type approval where the cost of installing these units doesn't go through the roof, because that's what we've seen with the classical nuclear industry, that this whole approval, both the time it takes to approve things, but also the cost of the approval is out of control.
Right.
And for example, there was a power plant that they built in Finland. It took 18 years to...
What was the name again? I forget. It was a
forget
huge plant.
Yeah, it was a really big power plant built by EDF, the French company. Right. And it took 18 years to build it and get it approved. And of course, if you look at just the capital cost of those 18 years, it's more expensive than our entire plant and fuel.
So
and
to some degree, that narrative that nuclear energy is way too expensive also has to do with the fact of the regulatory process and approval. Yeah. Otherwise, it would be far cheaper. I mean, it would be more. From what you just said, just to be so, you're in Switzerland now. Switzerland, for whatever reason, bought into this idea that nuclear is bad. We're kind of, while everywhere else the nuclear renaissance is going on, the Swiss and the Germans are still somewhat stuck in the old paradigm, and hopefully we can get out of that. If the Swiss government came to you and said, Thomas, we want to use your technology, how would you build that plant? Because there is the fact that, we actually in Switzerland have a good situation where we don't have that much solar and wind up and down energy yet, right? Germany would probably be more difficult, but how would you actually construct the plant to make it work for Switzerland?
Yeah, first we need to look at what are the energy requirements. The local, if it's electricity, the local grid or the local factories that are going to use that energy, like what is that customer demand look like in the next 25 or 50 years, and then based on that we will sort of figure out what will it cost to deliver that. And like I said, it depends a lot on what the customer is. It also depends a lot on that approval process. If that approval process take 18 years, it's definitely not $20 per megawatt hour, I can tell you for sure. Right. The assumption is that it's a lightweight approval process. Like when we built originally, most of the reactors that run today were built back in the 60s and 70s. And some of those early reactors that are still running now, built back in the 60s, they were approved in less than a year. And of course we can do that again. And they have been running safely for 60 years now or
Right.
even more. So of course we can do that again. And that's what we expect. If we are to meet that low price point, then we need an approval process that takes less than a year.
How probable do you think that is? I mean, with the approval process, I mean, if you look at the approval process today with the technology that the regulator is used to today, and now they see your concept and Copenhagen Atomics technology and the onion core, will that be too different, or will that be a completely new animal to them where they would have to learn it?
It's pretty much a new animal. Those people who are used to regulate nuclear energy or nuclear power plants, they need to educate themselves, or we need to educate them in how this is different and how it works and how the risk profile is different. So a lot of education has to happen. And we're already doing that today. We're inviting people from regulators around the world to come to Copenhagen and see what we're doing. And I think this will just increase over the next 5 years.
Right.
So we're already sort of pushing on that. But I also want to say that that target price I mentioned of $20 per megawatt hour, I don't think the very first commercial reactor will hit that price, because I think in the beginning it will take longer to get things approved.
Right.
That's sort of when we are up to scale and can do mass manufacturing and mass installation. That's when we hit that price point. And we believe that will happen somewhere around 2035.
Right.
So it's not that far away.
It's not that far, actually. And so even at a higher price range, if you could calculate the price coming down over time, you could actually say, let's do it. So how soon could you actually get started? So going back to my question before, let's say the Swiss government, the Swiss people decide, yeah, we want to go back on the nuclear track, and we like that technology, and we want to feed the electrical grid with it. And maybe we want a combination of the electrical grid with our lakes, with the dams, right? Could you do that? And how soon could you actually build something like that?
Yeah, I mean, technically we can definitely do that. There's a lot of discussion in the approval process. Yeah. So we believe that we can have the first commercial reactors ready from 2028. So
that's 4 years away.
Yeah.
Assuming the approval process was quick enough.
Yes.
So that's a huge opportunity for Switzerland and other countries as well, because instead of then building too many of these natural gas type plants, as kind of a bridge, or going back to coal and everything, I mean, that's not long at all. That's,
and I think what will happen is that, it takes time to scale up any mass manufacturing, whether it's iPhone or cars.
Right.
And of course, for us, it will also take time.
Right.
And I think because it's low cost, then we will favor the countries where we can install something fast over the countries where it takes longer.
Right.
So only certain countries that have a fairly fast approval process will have access to this technology in the beginning.
Right.
And then as we get further down the road...
This should be a shout out to our Swiss politicians and regulators. They should move on this.
Yeah, and I mean, we're talking energy supply here, and some of these other forms of energy, whether it's wind or solar farms,
they take a long time as well.
They take a long time, and they cost billions of dollars. And since we build, own, and operate,
they're subsidized heavily.
Yeah, and because we will build, own, and operate the power plant, so the politicians or whoever it is actually don't have to come up with the money to finance the power plant. But of course they have
not in advance. It's just that regular payment.
Yeah, but of course they have to invest a little bit in the regulatory system and educate the people in their regulatory departments.
If you're here in Switzerland, I'm not sure what I can say here, but maybe you can talk a bit about the fact that you are actually in Switzerland also because you're very interested to do something in Switzerland. Yeah. And I'll leave it at that. I don't know what you want to, how far you are advanced on that front.
I can say a little bit more. So we work with a number of national labs and universities around the world. And here in Switzerland, there's the famous PSI, or Paul Scherrer Institute, which is sort of a national lab here, that they have had a number of reactors on their site throughout the years. And they are active in nuclear research. And we've made an agreement with them to do some research together with them and test some of our equipment, even a large-scale test. So that's of course.
What do you mean by a large-scale test?
I cannot go into details,
Okay.
but hopefully later when we get a little bit
right.
further into the research, we can release more information about the test and the results and so on.
Okay.
But it is of course important that we test these technologies before we start building nuclear power plants.
Right. Right.
And
That's good news if the Polish Air Institute is involved and working with you guys. That's very good. How far advanced are the like? How much work did they do to already review and assess your technology?
So specifically, our type of reactor is called a molten-salt reactor. It is sort of a special type of nuclear reactor. And Pedersen Institute has been part of a group of universities and national lab in Europe that have done research on this type of technology for more than 10 years.
Yeah.
And I've been here also many years ago, I think it was 2016, at a conference where a lot of different people were discussing how to advance this molten salt technology in Europe. So Pedersen Institute has been active in this for many years, and therefore they don't start from zero, whereas what we see in some other countries is that some of those places pretty much start from zero. So that's great opportunity for us to work with them.
Yeah, yeah. The maybe going back to the mass manufacturing, just something I mean, part of mass manufacturing, which is really difficult, is the supply chain aspect of it. It sounds like you will have quite a bit of thorium, but you'll also have some lithium and uranium. Maybe in the future, at some point, it sounds like spent fuel rods, not in the beginning. How difficult is it actually to build or have access to thorium at this point? I mean, if you actually were to scale it up, is there mining in place at this point?
There is already mining where we get different types of mines around the world, get lots of thorium out of the ground, but it's not refined because there is not really a market for thorium today. There is a tiny market, but it's a few tons per year, where we need thousands of tons of thorium. So it's on a completely different scale than we needed. And currently we are making agreements with the mining companies and chemical companies to sort of start that supply chain and start refining that thorium out of the mines. And what we need is something called thorium fluoride. It's a chemical. It's a white powder when we get it. But those companies who convert it from the dirt out of the ground to thorium and then to thorium fluoride, those process lines have to be put in place. And we already signing contracts this year with.
Are those chemical companies, or what kinds of companies?
It's mining companies and refining and chemical companies.
Okay.
There's something called fluorination and chlorination. There's lots of chemical companies around the world doing that for many different types of elements or chemicals.
So you're in the negotiations of setting up those contracts so that once you start ramping up, they would actually then be prepared to do that.
Yeah.
How much lead time do they need for you to let them know? Now we're
we're
coming.
It's typically several years. I mean, right now we are signing contracts, and then that sort of agreement so they can get some capital and know that there's a customer, and then they need to build the process line and get that approved. Usually, when they operate with thorium and uranium, they need approvals by the authority to run those lines. So all that needs to happen, and then once it's up and running, we get samples and we have to check the quality. And once all of that is good, then they can sort of start to scale up. But it takes several years to get a supply line like that up and running. And of course, in the beginning,
so your volume won't be that high. So as you scale up, they'll be scaling up.
Yeah.
And the contract is arranged in a way where your scaling up is synchronized to some degree, and they will be able to scale it up. Is that difficult?
So I think we already talked to more than 20 mining companies, and now we have verified that only a few of those companies actually get more thorium out of the ground already than what we need when we have a production line that makes one reactor every day. So the thorium is already coming out of the ground. The problem is more to get it to that chemical state that we need, and
with the salt mix. If if you compare your technology at this point, to me the USPs seem really clear. You know, the mass manufacturing, the energy as a service, the safety aspect. I love the recycling idea, although that seems a bit further away still, but that too as a potential. What are your main competitors? Like, who's out there? Is there anyone out there doing something similar? Or it seems like your business model for sure, but also the onion core is very unique.
Yeah.
I haven't seen anything like that out there.
I agree with you. We are sort of we're definitely in a different corner of the market than all the other nuclear players. Yeah. Most of the other players, like we talked about earlier, they are going after electricity production for grid applications, mostly in maybe Europe and in North America. But we are sort of in a completely different corner of the market where we're competing with coal and natural gas in those commodity type production environments. So it might be converted into electricity. In the case of ammonia, you need to convert almost all the energy into electricity, and then you use that electricity to split seawater so that you get oxygen and hydrogen, and then you use that hydrogen to create ammonia. So
in German we call that electrolyse.
Yes, exactly.
What is that in English? It's
electrolyzers or
electrolyzing. Okay. Yeah. So you actually create the energy to then use for the electrolyse to turn salt or seawater into hydrogen, is what you're saying. Okay.
And I think there's an important point here. So if you look at all the food production in the entire world, if you didn't have fertilizer, you could only make half as much fuel in the same land, same amount of land. Right. So you could say half of the food you eat, that energy comes from ammonia. Ammonia is the most common fertilizer. And we don't think about that.
True.
And that ammonia today, almost all of it is made from natural gas. So when you go home tonight and eat your dinner, half of that energy that you get out of that,
salad.
it comes from natural gas.
Interesting.
And that's of course what we want to change. We want to change that so that energy that you eat comes from thorium. But that will take a number of years to get there, because that market is huge. The global ammonia market is just as big as the global electricity market.
Right. And it means that by focusing on that market while other technologies focus more on the electrical grid market, you can actually really help solve some of the overall energy problems too.
Yeah.
If I compare, we're in Switzerland right now, if I compare your technology to Transmutex, which is a Swiss company, although they have to work on what they want to do outside of Switzerland. How would you compare their technology? How is it different? They have some molten-salt aspects to it, as far as I understand.
Yeah, I have to be honest and say that I don't know all the details of the system that they try to develop or sell. But one of the key components in their system is a particle accelerator, just like CERN, where they accelerate particles, and then they use those to run a nuclear reactor.
Kind of like as a catalyst for the fission then process.
Yeah. Okay. And one of the things they say is these high energy protons that they generate, which eventually is converted into high energy neutrons, and that's why their name is Transmutex. They can transmute some of the nuclear waste, for example, plutonium, into something else. We can also do that.
So they also have an aspect of recycling. That's great.
So we can also do that in our reactor, but we do it in a completely different way. Yeah. So sort of we're trying to solve that problem of getting rid of nuclear waste using completely different methods.
Right.
But of course they use some of the same materials. They use uranium and thorium, and it is a nuclear reactor.
But in their case, it's not modular, and it's not. I guess in their case, it's more of a larger. I assume if there's a particle accelerator, you can't do that in a shipping container, I assume.
Yeah, I also think so, but I don't have the details too.
Right.
And I haven't heard from them what price level they are targeting. Right. But my belief is that if you have a nuclear reactor driven by an accelerator, your price cannot get below $100 per megawatt hour. But that's just my belief. I don't have any proof of that.
Interesting. So when it comes to, again, I mean, currently when we think of nuclear, and I think that's the narrative, or the common man in the street, when he hears nuclear, he thinks of these huge plants. He certainly doesn't think of shipping containers. There's also a lot of talk about something called SMRs, so these small modular reactors. And I'm not totally clear on what that actually is.
I'm not clear on that.
You guys are not, you're not an SMR, right? I mean, you would not want it because the category is not really clear, I guess.
Yeah, so there's a number of labels used in the nuclear industry.
Yeah.
And you're absolutely right that one of the labels used a lot in these years is called SMR, or small modular reactor. Right. And we have decided that we don't want to use that label for our technology. Right. I've seen other people use it on us, but that's their choice. We don't want to use it ourselves because SMR was sort of in the early days, it was coined as a modular reactor, a little bit like we talk about here, a unit that you can make in a factory, and that unit you can move on a truck or a barge or something.
Right.
And then you install it at a site, a reactor site, and then you run it there. That was sort of the idea, that you don't have to do local construction.
Right.
And then there was another idea, especially early on in the US, they say these small modular reactors have to be below 300 megawatt electric output, otherwise they're not called small.
Right.
But then this whole thing changed.
So far you guys would still qualify as an
sort
SMR,
of, sort of.
Right?
But then the whole thing changed in the UK, because the UK defined small modular in a completely different way. Right. And then they have another concept called ANT, Advanced Nuclear Technology, which ANT fits better on us, and small modular reactor in the UK does not fit on us. So it depends on who you ask.
So what's the aspect in the UK that changed?
I think it started with Rolls-Royce. Rolls-Royce wanted to build what is called light water reactors, and their size of their reactor is roughly 450 megawatt electric, which is sort of the average size of the reactors in the world today. But there's also these large reactors that are like 1 gigawatt, so twice as big, 1,000 megawatts, which is also being built. So I think they wanted to signal that they were smaller than the big plants, hence small.
Okay.
But then the Rolls-Royce is not completely factory built. It's a lot of that construction is on-site construction. Yeah. So that's
exactly
sort of
where I get lost, because if there was a study by IAEA recently on SMRs, and in the end I didn't really know what an SMR is after looking at that. And
study. Then the thing is also, a lot of people have started using the SMR term on the type of reactors that are solid fuel reactors, also light water reactors. Right. So same as Rolls-Royce or Hitachi BWR or NuScale or these other basically light water reactors. So those are the classical reactors, but of course maybe in a smaller version.
Right.
But that's why the UK invented that new term, where it's advanced nuclear technology, which is supposed to indicate that it's not small modular reactors. Right. It's new and different advanced reactors.
Totally different concepts.
And then, Copenhagen Atomics and Transmutex would fit in that category, ANT.
So Transmutex would also be an ANT in your view. Okay,
but,
interesting.
So we don't use that term because people have a different opinion of what it means. Right. And there's another term also called Generation 4 reactors that we've decided not to use.
Okay.
I
thought you guys were a fourth generation.
Yeah, but so let me explain.
You're fifth generation.
Not really. So back in the 1950s, when they started building the very first reactors, that's sort of Generation 1.
You're talking about the Oak Ridge reactor now?
No, more like the first commercial reactors.
Oh, just the light water reactors.
Yeah, light water reactors. Yeah. So they were considered Generation 1. And then there was 2 and 3 and 3 plus. And so the 3 plus started being built in the 90s or maybe a little bit after 2000. Mm-hmm. And then some people back in the 90s decided that we also need to have sort of a new type of reactors that is not light water reactors. That is sort of all the advanced reactors that are different from all those light water reactors, Generation 1, 2, 3, and 3 plus. So they called it Generation 4. Right. This was back in the 1990s.
Oh, okay.
And none of those were built back then. But some of the ideas were already I mean, those ideas were not new. Those ideas were back from the 60s.
Yeah.
So the ideas itself were old, but there were some people in the 90s saying, let's call that generation 4. Right. And then a little bit later, after year 2000, I don't know exactly when, but let's say 2005, they also added molten-salt reactors to that category. So now there were 6 different types of reactors in this generation 4 family.
Yeah.
And
including still light water reactors as well?
Not really, but there is a supercritical steam reactor, okay. Which you could say is a light water reactor to some extent. So at least it smells a little bit of it. So it's, but now lately there's been companies talking about their reactor being more advanced than those reactors proposed back in the 90s, and some of them back from the 60s.
Right.
So they call that generation 5. And that has not been recognized sort of internationally as a new category.
Yeah, I haven't seen that yet.
No, but it has been talked about at conferences.
So ANT, the Advanced Nuclear Technologies, would you consider yours and Transmutec's to be generation 5, or you just basically don't want to be put in a category, is what I'm hearing?
If there is another company that can build one reactor every day, and they can get the price, say, below $25 per megawatt hour,
right.
Then we would fit in that category. and
right.
I don't see any of those other companies being anywhere close to that.
Interesting.
And people have proposed to us we should call it generation 6 or 10 or but we just call it Copenhagen Atomics waste burner and the onion core. It's sort of in the beginning, when we had the different phones, they were called smartphones, but also people try to call it iPhone. Right. And I mean, I think we should go by the name of what we built.
The technology you're
building. And eventually, if there's 5 companies making something very similar to us, then we will talk to those 5 companies and maybe agree on some sort of category around that. But I think it's too early. There's no one else in this category right now.
So basically, when I listen to you and when the way you describe the technology, there's a high certainty in your, there's a high conviction that this all works, and I think that conviction is from talking to you. I think comes from the fact that you have done a lot of actual testing with the materials, with the molten salts, with the circulation of product and so on. And you actually have, so it's not like, it's not a concept, it's you have those materials and the machinery and the infrastructure, you have the factory, so you're far advanced in that regard. One of the things I wonder about is in all of the testing, you have not been able to actually test the actual fission, right? So because there you need that approval first.
Yes.
How can you know that it's going to work?
Yeah. So first of all, there was a molten salt reactor running back in the 1960s, from 1965 to 1990. Yeah.
Okay.
It was called the molten salt reactor experiments, or MSRE.
Right.
So that showed that the idea
That's
behind...
in 1960 in the US.
Yes. So this shows that the idea works, that there's not any sort of physics that doesn't work, but of course our reactor has a little bit different shape,
different
dimensions, and a little bit different fuel composition.
Right.
And of course we have to prove that also works.
Right.
But back in the 60s they didn't have computer simulations. They couldn't really simulate it, and there's many things that they didn't know, but they still got it working. Right. But today we have really, really great nuclear simulation tools, software tools that can simulate all kinds of details, and we've used that very, very extensively, and that's why I'm 100% sure that it will work when we turn it on. So I think there's no questions about whether it will turn on and generate energy, but there's other questions about these material degradations, like how many years can those materials last in this? There's corrosion.
That was back in Oak Ridge in the 60s. That was one of the key problems with that site, right? The corrosion aspect, or
yeah, I mean it is so. So this is also why you see sometimes on the internet you see people saying, no, molten salt reactors, it will not work. It takes 20 or 30 years before it works. But that's because the people who say that, they are under the assumption that molten salt reactors have to last 50 or 60 years, just like the last light water reactors
Right.
last 50 or
Right.
60 years.
Right.
But that's not the case. I mean, most of the companies who suggest or wants to make molten-salt reactors, they want to run them 4 or 5 or 6 or 7 years. Right. There's a few that talks about longer timescales than 7 years, but most of them are less than 7 years. And that's because we know that this high temperature is very difficult for the materials. Right. Also, the corrosion is an issue for the materials. Also, if you have a reactor where you have to turn the power up and down, that means you have thermal cycling. And these materials, it's difficult to make them last long if there's many thermal cycling or a lot of thermal cycling. So that's another reason why we want to run our reactors with factories that just run 100% all the time, instead of having a electricity grid where you turn it up and down according to wind and solar.
Right. So, but I think what's important to understand for those listening is that you have to, when you talk about the reactor, you're talking about the module,
yes,
not the plant. So it sounds like the plant can actually run for a long time, but the module you would exchange, I think, after 5 years.
Yeah. So that's sort of the onion core and the pumps and the heat exchangers.
That's
those components,
they would be kind of deposited as part of the factory of the plant.
Yeah. But the overall building and the most of the steel, there's a lot of steel in there to protect the reactor. All of that can last for more than 50 years, maybe even 100 years. But we will try to get an approval for 50 years in the beginning, and then when you get close to the 50 years, you can maybe get extensions. And the thing is, the reactor containers itself, with all the technology, that is replaced every 5 years. Right. So when you're 50 years down the line, then your technology is still only 5 years old. So that's why we think it could potentially run much longer, maybe 100 years. But I don't think we could get an approval for 100 years right now.
Yeah, probably not at this point. Maybe going back to the corrosion topic, I think you guys have actually also invested quite a bit of time and research in the concept of, creating salts that don't corrode as much. Is that correct?
Yes. So I mentioned that MSRE reactor running in the 60s, but I forgot to mention that we have already built full-scale reactors, and we are testing those in Copenhagen. We're not allowed to start the chain reaction, but we can test them in full scale, and we heat them up with heating elements, electrical heating elements. And so we test everything with pumps and heat exchangers and onion core.
And the salt.
And the salt and corrosion and everything. So we're already doing those tests to verify that everything works as it should. But of course we don't have the license or the approval by the government yet to turn it on. But we expect to get those approvals within the next 2 years of roughly. And then we will turn it on, and like I said, I'm 100% sure that it will work. The question is more about how long will those materials last, how much degradation will we see.
Is it the advance that you have made in terms of material science, or is it the salt where you've created? I mean, where have you been able to actually reduce corrosion or extend the lifespan of the systems?
Yeah. So actually, there's a little bit to that story. The reactor that ran back in the 60s in Oak Ridge in the USA, there was a guy from Denmark. He was young back then. He went there and did his post-doc studies. He had his PhD, and then he went there and did his post-doc studies at Oak Ridge. And he worked with purifying salts. This is back in the late 60s and early 70s. And then he came back to Denmark.
So he was part of that team that actually ran that nuclear plant, or was it?
Well, not the reactor itself, but the chemistry department.
Okay.
And then he came back to Denmark, and eventually he became a professor at the Technical University of Denmark.
Okay, that's where you're linked to the university.
Exactly. Okay. So he worked there for his whole life. He's now 85 years old. So he has worked for 5 decades improving these technologies around molten salt. And one of my co-founders in Copenhagen Atomics, also called Thomas, he did his PhD in that group at the university. So he already did a lot of research on molten salts and corrosion, but for other industrial processes. I mean, there was no molten salt reactor company in Denmark back then, so their research in the university was to use this in other industries. And so they already knew a lot about corrosion, and that was a huge help for us to basically stand on the shoulders of giants when we started. And then from there on, we refined the process so that we've been able to scale the process up and make very large batches of salt production at high purity.
Yeah.
I think we are the best in the world at making these pure salts. We compete with some of the universities and national labs around the world. We send samples to each other and sort of compete on who has the best quality of salt. And in most of those tests, we are number one.
Interesting. I mean, when listening to you, it's actually, I mean, what's the bigger part of what you do? Is it physics or is it chemistry? It sounds like it's chemistry and material science, really. Or
it's a big mix of everything there.
Yeah.
There's a big chemistry
Engineering
department,
also?
but there's also a reactor design, and the reactor design is actually, a lot of that is simulation. So those are software developers that are improving the software tools so that we can improve the reactor design. But there's also a lot of physics in that. If you don't understand the physics, you cannot make the software.
Right.
And then there's people building systems and
mass
testing.
manufacturing and testing.
Yeah, we don't do that much mass manufacturing yet.
But you have to prepare for that, right?
True. But so we built these full-scale reactors, and we need electricians and welders and everything for building those, and we need to run them. That's also quite complicated. So half of our staff is sort of in the workshop building stuff and testing stuff.
Yeah. When we think of mass manufacturing in the future, how much of that will be manual labor, and how much can you actually use robotics in that process?
So the way I think about it, it's like car factories. I mean, all the different components in a car is made at some other factories, like the seats and the wheels and the crankshaft and whatnot, the brake discs. So for a car factory, you need thousands of sub-suppliers that all make different components.
Right.
And what we see today is all the components, or almost all the components we need for our reactor, they are made in CNC machines, meaning sort of fully automated machines, whether it makes electronics or milled parts for the pumps, or, I mean, all the different components are made on machines in different places around the world. They use laser cutters and robotic bending machines and stuff like that. So I would say a lot of that is already automated, and eventually our assembly line will probably also be automated, but at the current scale, we don't need that. I mean, today it's manual labor, but I do think we are moving towards industry that is more and more automated. And I mean, we make a lot of electronics and sensors and control systems, and you probably know from iPhone and other. I mean, all of that is completely automated. There's it just runs inside of machines. And
so, but you're gonna. How much do you know already? How much of the assembly material is going to be outsourced, and how much are you going to produce? I mean, Tesla, for example, if you compare there, they actually are going more and more towards actually producing a lot of the parts and things themselves. Do you see yourself going in a similar direction, or what's your expectation?
We debate that a lot in the company. So we decided early on to focus on pumps. So we have developed our own pumps, and we spend a lot of money and efforts on developing that. We get all the parts for the pumps from sub-suppliers, but we assemble them in-house. So we have a small team of people who build these pumps.
Right.
And it's a little bit like building a car engine. I mean, it's a similar process. And the volume of that production right now is batches of 20 or 50 units per batch. So that is manual labor to assemble that. But eventually some of those steps are being automated, but maybe we need to get above 100 units per batch before it makes sense to automate that. Another thing that
right now a lot of the work is still prototyping, is what you're saying, or?
Yeah, I mean, early prototyping is when you make 2 or 5 per batch, but when you get to 20 or 50 or 100.
Is that where you are today?
That's where we are with many of the components. It's sort of.
Are you selling them, or are you?
So mostly we use most of it for internal testing for those reactors that I talked about. We also have a number of test loops where we test components. Before we can put components into a reactor, we need to test those components separately. So we do a lot of testing. Actually, we believe that we've done more testing in Copenhagen Atomics than all the other molten-salt reactor companies combined. We have a huge department.
Because you're producing these parts.
And we also have these test systems where we can test many test hours.
Okay.
And so another thing that we've decided to make is, in order for those salts to be high quality, we need something called lithium-7. So it's the same lithium that you put into batteries, but it needs to be, again, purified so that it becomes lithium-7. And that process we've decided to build in-house.
Okay.
So certain things where we say we can have a huge advantage over sub-suppliers or somebody else.
Quality or cost-wise.
Yeah,
also.
then we do it in-house. But for example, heat exchangers, that's something we just buy from sub-suppliers.
You can use the standard.
Yeah,
it's more of a
or even this
commodity in the
onion
overall.
core that I talked about.
Yeah.
I mean, we specify those CAD drawings and then we send that out to sub-suppliers and they manufacture it. So they send the whole onion core to us and we just install it. So I mean, that's made by a sub-supplier and they have a mix of automated machines, CNC machines, but they also have manual labor.
Right.
It's a mix.
Thomas, this is fascinating. Maybe, before we kind of go into closing questions, how did you get into all of this? I mean, it sounds, I know you studied electrical engineering, but you're basically you're mastering a lot of different disciplines that you need to cover.
Yeah. Maybe it's a long story, but I'll try to make a short version. So since I was a teenager, 10, 11, 12 years old, I had a huge interest for how things are made in general. Yeah. And I like to go to museums, and especially technical museums, and I like to read books about how a car works and how a jet airplane works and how a computer works. And when I got a little bit older, I also wanted to know sort of the history of how that was invented, like the people behind those inventions. And when I graduated from university, you were absolutely correct. I was trained as an electrical engineer. My very first job were for Nokia, and this was back when Nokia was sort of in their heyday, and they were the #1 technology company in Europe, and it was a lot of fun as a young engineer to work there because they were doing really well at the time. And
I think my first phone was a Nokia.
Yeah. So that whole history of how was the mobile phone invented, who were all the different people involved in that, and what were the components that they need to invent to make a mobile phone like that you can have in your hand. I was very interested in that. So since I was a child, I learned about how things are made, and of course at some point I was interested in how nuclear reactors are made. and I was at right around the same time as I was interested in nuclear reactors, I was also interested in fusion and how do we solve the energy requirements of the world, energy supply. And at that time, I was like 40. I had a lot of experience with how everything is made. So I went to some conferences about nuclear energy, and I was able to ask sort of the right questions about how this stuff works. I also went to a number of reactors that are now museums, where you can get into the reactor and see how it's constructed. And just by doing that, I realized how this whole thing worked, and that helped me a lot in understanding how you would then build this next generation of reactors. And I was very, very fortunate to meet some people, like I already mentioned Thomas, who had a background in molten-salt chemistry, because honestly, I don't know very much about molten-salt chemistry. And I met some other people who also had some of the things that I didn't know about. So together we were 4 people who started the company, Copenhagen Atomics. And between us, we had enough knowledge to get started. And then once it was started rolling, we could hire more people with the skills that we didn't have. So it's just a long journey. But to be honest, for 30, 40 years, I've known a lot about how you actually invent new technology and how you go from a prototype on your kitchen table to mass manufacturing. So yes, that's just part of my education.
I have to ask you this. I mean, you just mentioned fusion. Why did you go to molten salt, onion core reactors instead of fusion?
Yes, so I looked at fusion and I thought about investing. So I had made a few startup companies, and one of those I made a fair bit of money, and I invested some of that money in other startup companies. And some were good investments and some were really bad.
What was your first startup company?
The first one was Together with another guy, we made the world's smallest charger for mobile phones. Okay. So maybe you remember back in around 2000, the chargers for mobile phone were these big bricks they were very heavy.
Yeah.
And we were part of inventing sort of this new type of mobile phone chargers that are very small, like the type you have today. Yeah. So we made a company and we sold that to another company making these type of chargers. You also have
who did you sell it to? Can you say that? Or
what?
Can you say who you sold it to?
It was a Chinese company that manufactured these types of chargers. Okay. And they manufactured that particular product for 10 years before it was discontinued. Yeah. But that was one of the companies that I helped start. Right. I was also part of another one where we made 3D scanners and 3D printers. That's a long journey, but we started by making hearing aids. So, hearing aid you put in your ear. Yeah. They have to be really small and they have to fit in each person's ear. Mm-hmm. So we had to make a scanner that could scan the shape of that and then put electronics into it and print sort of the plastic casing and make it into a hearing aid component.
You're the modern day inventor.
Yeah, well, I was fortunate to be part of a number of those companies. I was also working in Silicon Valley for a while, and made another startup company where we did some software, made some money from that. Anyways, long story short, then this idea came along, and some of those money I made, I also invested in wind energy. Okay. And at the time when I did that, I worked for the Danish, the big Danish utility company is now called Ørsted. They were called something else back then. Yeah. But I worked for them as a consultant, and I learned a lot about the electricity grid and how that whole thing worked. Mm-hmm. And this was at the time also that I looked at fusion. And after researching on fusion, I decided that I didn't want to invest my time or my money into fusion. I didn't think it was right for me. I still want the world to research on fusion, but I have to be honest and say from the research that I've done, I don't expect to see a commercial fusion plant in my lifetime. I think we should continue to research on that subject, but it's not a short-term solution in my opinion. Most fusion power plants or most fusion machines, they need to take deuterium and tritium and smash them together. Deuterium you can find in seawater. It's expensive, but you can get it. We also use deuterium in heavy water. But we use a lot less than what you need in a fusion reactor. But then you need tritium, and tritium is really, really difficult to find on this planet. And some people say that there's only enough tritium on this planet for one fusion reactor. So what are you going to do then? And then one of the things you can do is you can make lithium-6, and then you can take some of those neutrons in a fusion reactor and convert lithium-6 into tritium, and then you can use that tritium. But getting that whole process to work economically with like a great fuel price is very difficult. So that's why I don't expect to see any commercial plants anytime soon. But I mean, I'm happy that there's other people who believe in it, and they spend their money and their time to try to make it work.
But in the shorter to medium term, you don't expect it to be functional. And it sounds like, I mean, with the thorium molten salt reactor, you actually have a technology that you can use, which actually already worked at one point. Yeah. So now you're like optimizing it. How did the onion core technology come about? Was that something you came up with, or was that a concept that existed?
I mean, other people already knew that it was a great idea to have a blanket, a thorium blanket, and to have sort of the fuel in the middle. And then we did a lot of simulation, and my co-founder Aslak came up with this idea of the onion. And of course, we did a lot of simulation to figure out what should be the right size and everything. But there was a lot of different ideas.
Was that before you guys founded already? So when you founded like 10 years ago, right?
Yeah, it was in the early days.
So the concept you already had when you guys founded, and it was 4 founding partners, right?
Yes, the concept of a thorium reactor with a heavy water moderator and with a thorium blanket and this idea that it should be in a shipping container form factor and mass manufacturing. those ideas were already
already
there
in
before
place.
the company was started. But some of the details about pumps and
A
onion
lot of
core and
details,
some
it
of the
seems.
a lot of the details also
Yeah.
about the corrosion, making these purified salts. All of that came sort of down the road in the first 5 years.
Thomas, we have to come to an end, unfortunately. I mean, this is I could continue asking, and there's all kinds of things I wonder about. But if you look at the big picture outlook, and you look at there's currently, we say there's a bit of a renaissance going on in nuclear. So there is hope that nuclear, can, and especially future and technologies like yours can really create a better future. Where do you see the biggest risks and the biggest challenges moving forward?
I think it'll be difficult for many of these new nuclear companies to actually get their reactor financed and approved and get the first 1 or 2 units up and running. I think that's a really difficult milestone or a roadblock to get over. Once you have had a few commercial reactors running, I think then it's a little bit more clear how you can improve it and scale it from there. But I think it's really difficult to get the technology off the ground for any of the companies, including our own. You also asked about risk. I mean, a lot of times we say that if there is a new nuclear accident somewhere, some reactor blows up in Russia and it gets all over media, then it will be really difficult for us to...
The momentum could be lost.
Yeah, it's difficult to raise financing for maybe 5 years, which would be devastating for us. Maybe it would not kill our company, but it would definitely hold us back. So that's of course a risk that there is. There's also a risk that there's a big financial crisis where it becomes difficult to raise
get funding.
capital. Yeah.
Right.
So, but life is risk.
Maybe the very last question for me is obviously, so what's the chance that we bring Copenhagen Atomics to Switzerland?
I mean, that's why we're here, and we hope, of course, that this collaboration with PSI really help us to make a breakthrough and get this technology closer to the market. And I mean, it's difficult to say at this point whether we will install commercial reactors in Switzerland, but it's definitely a possibility. But I also think that there's a lot of smart people in Switzerland that could help us build this technology. I mean, the mass manufacturing and some of the technologies behind sensors and other things. And also in finance, that's also sort of we need a lot of work on that part.
Well, I hope a lot of those smart people are watching this video, and that we can actually, everything I hear, I just excites me about the possibilities of what you guys do. And thank you so much for your time, and sorry for posing so many questions.
No problem. Thank you for
really
inviting.
Yeah, thank you, Thomas.